In this video, we'll explore how to build a hierarchical regression model for grouped data. For example, suppose we're interested in exploring the relationship between running time and age for runners in their 50s and 60s. To this end, we can utilize data from the annual 10-mile cherry blossom race. Each row contains the results for a single race for a single person. Check out the first row. Runner 1 ran the race in 84 minutes at the age of 53. This same runner ran the race in 74.3 minutes the next year at age 54. Thus, the data that we're working with is grouped. We observe multiple race outcomes per runner. For example, we observe 5 race outcomes for runner 1 at the ages from 53 to 57. Similarly, we observe multiple outcomes for runner 2 and the other runners in our sample. With this grouping structure in mind, let's specify our goal. We'd like to model a person's running time, Yij, by their age, Xij, where specifically Yij is runner J's running time in their ith race, and Xij is their age in their ith race. Our first approach might be to apply our usual normal regression model. In this complete pooled approach, we effectively ignore the grouped structure of our data and pool all of the race outcomes together. Specifically, we assume that running times y vary around some regression model, beta 0 plus beta 1x, with standard deviation sigma. Further, we put priors on our unknown regression parameters, beta 0, beta 1, and sigma. This plot illustrates the data points, along with 100 posterior plausible models of the relationship between running time and age. It also illustrates a big bummer. Mainly, notice that these posterior plausible lines run the gamut, including the possibility that there's no relationship between running time and age. This turns out to be wrong. That is, by completely ignoring the grouped structure of our data, we'd mistakenly conclude that there's no significant relationship between running time and age. Another drawback of this model is that it aggregates information across runners. Thus, whereas it might allow us to explore how fast, say, a 55-year-old or a 60-year-old might run, it does not allow us to explore how an individual runner's speed might change over the course of time. Consider the opposite extreme. Suppose we take a no-pooled approach, building a separate regression model for each runner J. Thus, in comparison to the complete pooled model, the no-pooled model allows each runner J to have a unique intercept and slope, beta 0j and beta 1j. Now, this might seem like a good idea at first glance, but it too is a bummer. First, by fitting separate models for each runner, we can't use our data or models to understand any runner outside of our specific sample. For example, we couldn't use it to predict your running time at age 55. Further, this approach underutilizes the data. When learning about any individual, we can't use data on other runners. This is especially silly when we don't have much data per individual. For example, consider runner 1. Laughing in the face of the evidence that most runners slow down over time, their individual model assumes that they'll continue to get faster. A hierarchical regression model provides a balance between these two extremes. Unlike the complete pooled model, a hierarchical model respects the fact that we have multiple data points per runner. Hence, it captures the individuality of these runners. And unlike the no-pooled model, a hierarchical model understands that data on other runners can provide information about any individual runner. That is, this model borrows strength from the other runners to learn about any individual. This is especially advantageous when we don't have many data points per group or runner. Let's consider the 3 layers of the hierarchical model, one at a time. As with any hierarchical model, we start by focusing on the within-group behavior. In our example, this means that layer 1 models the relationship between running time and age within each runner J. Generally speaking, these relationships might be described by different intercepts and slopes. However, to greatly simplify things in our first hierarchical regression analysis, let's assume that each runner J has the same slope, but possibly different intercepts. That is, As we can see from the lines here, some runners, say this runner down here, is faster than other runners, say the runner up here. So our different intercepts allow us to assume that different runners might be faster than others, but the shared slope indicate our assumption that they are going to slow down or change at the same rate over time. As such, our layer 1 model can be expressed as follows. For each runner j, running times y are normally distributed around the regression model beta 0j plus beta 1x with standard deviation sigma y. Let's zoom in on the parameters in this model. First, consider beta 0j. The j subscript reflects the fact that this parameter is runner specific. Here, beta 0j is the intercept for runner j, or essentially the baseline speed for runner j. For example, the runner up here has a higher intercept, thus a slower baseline speed, than the runner down here. Next, we can think of beta 1 as the global slope. Global meaning that it's shared by, hence describes all runners. Thus, for all runners, beta 1, the slope captures the typical change in running time per year. Finally, consider sigma y. To give some context to this parameter, consider this plot with the data and model for just one runner j. Within any such runner, sigma y measures the variability of the observed race outcomes, these dots, from the regression line. Essentially then, sigma y measures the strength of the relationship between running time and age within individual runners. The smaller the sigma y, the stronger the relationship. Notice also that sigma y does not have a j subscript. Thus, for simplicity, we're assuming that the variability or consistency from year to year is similar for all runners. Okay, layer 1 took care of the running outcomes within any individual runner. Next, layer 2 focuses on how the relationship between running time and age varies between runners, that is, from runner to runner. In general, model parameters with subject-specific subscripts are those that help us distinguish between different groups. In this model, the only subject-specific parameters are the intercept terms beta 0j. This notation indicates an assumption that the model intercepts, hence baseline running speeds, can vary from runner to runner. Some runners tend to be faster or slower than others. Specifically, we'll assume that these baseline speeds vary normally around beta 0 with standard deviation sigma 0. That is, we expect the intercepts to be around beta 0, but they'll vary a bit from there. In this case, we can think of beta 0 as the global average intercept across all runners. Thus, in this picture, beta 0 would fall somewhere at the intercept of these typical runners. Equivalently, then, we can think of beta 0 as the intercept, hence baseline speed, for the average runner. The baseline speeds for all other runners fluctuate around this average. To this end, sigma 0 is the variability in the intercepts from runner to runner, or between runners. Thus, sigma 0 essentially measures the extent to which baseline speeds vary from runner to runner. Combined then, the first two layers of this model assume that the individual runner models, represented by the light blue lines here, vary around the model for the typical runner, represented by the black line in the plot. And this black line is captured by the formula beta 0 plus beta 1x, where beta 0 and beta 1 are the global intercept and slope. And sigma 0 describes how much the individual lines fluctuate from this global. The final layer of our hierarchical regression model incorporates prior information about the global parameters, hence the relationships between running time and age. The global or non-runner specific parameters are those that don't have a runner j subscript. Here, those parameters are beta 0, beta 1, sigma y, and sigma 0. Let's first consider the intercept and slope regression coefficients, beta 0 and beta 1. Since the intercept and slope of a regression line can take on any value in the real line, we can express our prior understanding of these parameters using the normal model, which also lives on the real line. Finally, consider the standard deviation coefficients, sigma y and sigma 0. Since standard deviations must be positive, we can express our prior understanding of these parameters using the exponential model, which also takes on positive real numbers. In conclusion, our hierarchical model unfolds in 3 layers. The first layer models the relationship between running time and age within each runner j. The second layer focuses on the differences between the runners themselves. Specifically, it models how the baseline speeds vary from runner to runner. Finally, the third layer incorporates our prior information about the global parameters, hence the relationships between running time and age.